Welcome. So we're going to go through question 6. We're going to use our CAS to answer this as well. Let's give it a read. It says, let S be equal to this. Be the height in meters of an object at time t in seconds. Find the velocity at time t. I want to show you that you can answer this question without really having an understanding of what you're doing here. What you know is that you've been given this equation here, which represents the position of where it is, and we're talking about height instead of like I normally would just be talking about left and right, but we're talking about height now. It says find the velocity. We know that velocity is simply going to be differentiating that with respect to t, and we can use our CAS to do this. We can come here, open up our CAS, and the first thing I would want to do is just maybe define what S is. So I could go S of t, and then I could hit this button and this button to define 10 plus 15t minus 4.9t squared. And that's all nice and defined for me. Now I'm going to differentiate that with respect to t. The best way to do that is shift minus, differentiating with respect to t, S of t, hit enter. And there is my very first answer. So my answer for what the velocity is going to be is 15 minus 9.8t. And we're done. And it says find the velocity at time t, so we just don't sub anything in for t, we just leave it like that. You could write it as meters a second. Next, we want to find the acceleration. We know that the acceleration is simply going to be what happens when we differentiate our velocity with respect to time. So now we could come here if we wanted to, and I might do this just for because we're going to use it later, but you don't strictly have to do this. I'm just going to define that v of t is my velocity. So I'm going to go control this, that, and that's done now. Now I'm going to go shift minus, differentiating with respect to t, v of t, I'm going to get negative 9.8 equals negative 9.8 meters a second squared. And now we're done. We've answered both these questions. We've found the velocity and acceleration at time t. Now, if you want to click off this video, you can, but I think it's worth our while just to kind of consider what's actually happening here and what this is actually telling me. What this is telling me is that my velocity is 15 minus 9.8t. So if we consider that as a graph, so let's actually graph this on Desmos. See, we could do it on the CAS, but it's just easy if we do it on Desmos. Here it is. And you can see what it looks like. So I've got, this is representing, the blue represents the path of the ball that's being thrown up in the air. And I've also drawn in a tangent line. And this is really telling us the velocity at each point here. So as you can see, I throw it up in the air, it's stationary there, and then it falls to the ground. So that's kind of what we're picturing in our head. Now, I imagine what people are confused about, if you are confused, is why do I have a constant negative acceleration? How on earth does that work? Why do I have a constant negative acceleration? Wouldn't it be increasing at the very beginning? Like if you throw a ball up in the air, isn't it accelerating? Why is it always decreasing? It kind of boggles the mind a bit. But it makes sense when we consider the velocity at each point. So remember that my acceleration is the change in velocity with respect to time. So let's just consider a whole bunch of velocities. We know that if we start at v of 0, we're going to have a velocity of 15. So we have a positive velocity, it's moving up. And then if we then check out the next velocity, let's just go when the time is 0.5. Do you see how my velocity immediately decreased? My velocity immediately is decreasing as soon as it leaves my hand and is going up. The velocity is immediately decreasing, and as I keep on going, it keeps getting smaller and smaller. If I did another one, it's becoming negative now. And then I could go again, it's negative, it's an even greater negative. So what I really want you to appreciate here is that the change in my velocity is always going to be decreasing. It's always going down. My velocity is always becoming a lower number each time. And that makes sense when you consider our graph here. So I want you to really take note of the slant or the gradient of this tangent, which represents the velocity. Because remember, the velocity is just the derivative of the position equation. Do you notice how as soon as I start moving, the velocity or the gradient of the line is becoming less and less and less and less and less. It's decreasing until it becomes 0, and then it becomes negative. So it's always becoming less. So the change of the velocity is always going to be negative. It's always going to be negative, and that's why our acceleration is negative. And it just so happens that this is also the force of gravity working down on the ball. Because if you think about it, if you throw an object up in the air, you know, the velocity is immediately going to begin to decrease because gravity is working on it. So hopefully that makes sense out of what's happening here. It immediately begins to decrease. You couldn't throw something up in the air. Could you imagine the alternative? Could you imagine the alternative? Let's contemplate the alternative. If you threw something up in the air, and it kept on going, and it actually increased, it went, I mean, that makes no sense. When you throw something up in the air, you throw it, and it comes down. It always has to look like that. It's always, the gradient is always decreasing. Only if it's like self-propelled or something like a plane. Think of a plane. It's accelerating, it's becoming bigger because the velocity is becoming bigger. But if you got something like this, then the acceleration is always going to be negative because it's going down. The velocity is always becoming less and less. Hopefully that makes sense. I imagine that some people might find that a bit tricky, that idea, but hopefully as I've walked it through here, I've shown you a bit of Desmos, shown you a bit of Kaz, it's kind of made it a bit more sensible. All right, I'll see you in the next one.